1, 2, 3. So the record is on. So we were around, no, not here, here for the break, okay? So I'm trying to show you this, that in the real world, not only that you will not have a series of simple beams, but you have to have this continuous beam. That's why if you are driven to be a civil engineer, you need to know how to analyze this, but not in the sense that you need to know how to carry it out, but at least what you must know is the behavior, because it's not just in the structures, in buildings, you know, in soil mechanics, they have the more complicated structure to handle the soil pressure and stuff like that as well. So it's a basic of every structure that you can use with buildings, the residence, the water related or soil related structures as well. Okay, so before we go to the example, let me show you a couple of things. First thing first, we shall go back to how we name the beams, okay, because it's a worthwhile question from one of your friends. Generally, you know, I experienced this in the design classes, where if you have freedom, sometimes you use the freedom to carefree, and you know, things are not in order. So let's say we name beams with B, right? Because B stands for beams. So it would be nice to try to use the name B for beams, okay? And rightly so, you know, if you want to name the columns, you should use C, right? So that becomes C1, for example, but we're not going to do the columns this class, but you know, anyway. This perhaps I'd name C2, okay? Now in the old days, I started off working as an engineer in 1995. I think you guys weren't born yet. In Buddha's year, that would be 2537. Okay, I was very well taught by, you know, experienced senior, and let's say in naming stuff like this, if it's a continuous beam, as you can see here, I'd say the names would be B3, and if it's the same details and it's continuous, it should be B3 and B3 and B3. We don't change the name around because they are continuous beam. So let's say I'm going to call this perhaps B3, B3, and then B3. And then I can give details how, you know, the details of B3 continuous with B3 should look like at the column zone like this, or at the midspan. And if the detail at midspan, let's say this one is different from that one, if these two beams, the details at midspan, they are different, I may change this name to something like B3A, so that, you know, different details, I change the names. So when you proceed with the construction, it's very easy. And one more thing is this. When you look at this beam like this, we'll come back and work on it shortly. Things like this. Generally, I would not there. Okay, this is not the good naming, because actually this is two spans, you know. So I should not call it B2 in the old days. But let's look at this one. See, this portion is a cantilever. So whenever I have the cantilever beam, or this one, I would always denote with the letter C, so that I know this is a cantilever beam. Because in cantilever beam, it's pretty similar to cases when you have the fixed support, right? So you guys know your cantilever beam from the statics. It looks like this. So a cantilever beam, it always bends like that, right? your simple beam, for example, bends like that. So this is always a negative moment. This is always a positive moment. So that means the details, especially in concrete for reinforcement, is going to be different. Because positive means the tension is down below, correct? You guys had that from mechanics of materials, right? And for negative moment, tension is up here on top. So the details of reinforcement are always different. So that means by giving it a name like this, like B5C, to remind myself that this is the cantilever beam, I will always be aware of the fact that tension is up top, and you guys generally should have more reinforcement up top than at the bottom, because that's where the tension is, and concrete cannot take tension. And for general simple beam where you have the positive moment, it's a typical case where tension is at the bottom. So you know that in this case, the reinforcement should be more at the bottom than at the top. So to give it extra name like C, you would know, and when you check your drawings, you would, okay, I know that the more reinforcement should be on top. So let's say if the draftsman makes a mistake of, you know, turning it upside down, you would know right away, that should not be right. Okay, so that's the art of the name. And it's more than that, because it's not like every time you run into a different beam, you would give it new names. In that case, you may end up having like 60 names in one structural drawing, one set of structural drawings. So, you know, you go out and do the reconstruction and you look at the name of the beam. It's like 60, are you kidding me? So it's going to be a little bit crazy in that case. If the details are similar, you should consider using the same name. Okay. And if the details are different, maybe it's a good idea to help create the shop drawings to use different names. Okay. So that should explain how we should name the structure. Okay. So let's come back to this one. Now, when you see, this is only a part of the floor plan. You see, it's a two-dimensional top view of your structure. If you look at the building as a whole, as a three-dimensional, this, what you see here, and again, what you see here, you know, the entire plan you see here, if I draw the building, let's use a new page. If I draw the building, it becomes just a flat plate of one floor, correct? And then we would have, like, you know, columns, maybe at some point more columns, and then more columns, stuff like that. So you can see when you have just a flat plate like this as your floor plan, you can have more, you know, maybe because you have more than one floor, correct? You know, this floor plan or the flat plate itself cannot withstand the load that comes in this direction, or the horizontal load. When your building has to carry the horizontal load to make sure that everyone who uses it is safe, the beam system alone is not enough. You need the system where your structure will act together. That's why we need another system in the, you know, this direction. to help resist the horizontal load. So if I'm gonna draw just the pink one, you are going to have to learn the new system that we call the frames. Because beams alone in this picture like this will not be enough to help your building resist the horizontal load. Okay, that is why after you learn how the load can be transferred onto the system of the floor plan, the two-dimensional basic system, the next thing you need to learn is to learn how to take care of the simple system that will help your building resist the horizontal load. Okay, and generally, you know, building has many floors, so it means that your frame can be very, very complicated. Like this, with so many floors. And then generally, yeah, if I want to make it a determinate structure, I can give you a simple support system like this. So you have like 3 reactions, correct? But in the real world, you know, you don't have simple frame like that. You're just gonna have maybe something more complicated. And maybe the supports are like this. You know, that's the system of the real world. But, you know, we need to go step by step. So in this class, we're gonna start dealing with, say, a simple framing system first. For example, let's say remove that and that, okay? Maybe we're gonna start with something like this, okay? And now you need to know what it is. Now you see, we no longer have a simple beam. This is still a simple structure, but it is made of 3 members. Okay, so you have member here, you have member there, and you have member there. Generally, where the member is connected, we call it a joint. Joint with a T, so please mind your pronunciation, because joist is the system of the floor. Now this one is joint. Okay, I don't know why they have to use like 2 words that's really close to each other, but that's how life is at times. This joint generally is called a rigid joint. Okay, and now this member is just like one beam. This is one beam, this is another beam. But the difference between this and what you have here, you see, right here is also a rigid joint, but at this joint, it is also a support. So there is an unknown force coming from the support. But in this case, this is a rigid joint, but you don't have the support at the joint. So in terms of the structure, if you look at the structure, you have 1, 2, 3 reactions. So this is perfectly determinate. It means that you can go ahead and analyze the structure with your current knowledge because you can solve all the unknowns. The only problem is that there is more than one member in the system and they are connected by the joint, whereby, you know, the forces can be transferred from one member to another. Okay, so this is the general idea of the class. You know, we have the typical load transferring system starting from the 2-dimensional problem first, and then we move on to a slightly more complicated system where we have more than one member to form the structure that we generally call the frame. Because if we don't have this, there is no way that our structure can resist the lateral load system. Okay, is there any question about anything? We are about to get into the example now. So, okay, please hold on to your horses. Before that, it's hold on to your hat. Right now, it's hold on to your horses. Is there any question? What's the one more in the chat? Can you explain a little more how frame resists horizontal load? Okay. Let me try to do this again. If let's look at the frame. Internal load, we're gonna have to wait. Okay, when we get into the frame, I will demonstrate how internal load occurs. But I just wanna I thought about it for a second, you know. But and now you ask. But I say, you know, let's not flood you with too much, you know, of so many things. We start off the simple load transferring system of the 2D floor. So let's keep it at that. But you know, I'm gonna try to explain a little bit more about the system first. So let's say if you have just the floor, when I draw it in 2D, let's say all the columns and all the beams do not act together as a system. You will only have the floor like this. Let's say if you don't have columns, okay? When you have the floor, instead of looking at from the top view, I now look at the side view, okay? So the floor becomes a flat sheet like this, correct? Let's say, I should say side view. Side view of the floor. So when the load comes to the side, well, what's going to happen to this? It's just going to blow by, correct? So you need something of a system to help put everything together to form a structure. So with the floor system alone, you know, there is nothing to help resist the horizontal load. You need to have something in vertical. So in this case, we put all the floors together by columns. But if you put the columns and the floors together without the rigid joint here, it's not going to be stable. Because let's say if I have a frame like this, okay? And then I have the floor, just like what we talked before. And then I connect the floor to the beam by, you know, let's say the floor is a simple beam. This system that you see now, this dark blue one here is, ladies and gentlemen, unstable. Because you have learned from Ajahn Julaput's class that when you have the hinge, that's when you have the extra equation, sigma moment equal to 0, correct? So now, because this structure is determinate, so the degree of redundancy, the number of unknowns is 0, because you can solve it, right? So it's 0 degree of redundancy. Oops, sorry. Bad handwriting. Excuse me, it's like so many things. So with 0 degree of redundancy, that means you have 3 equations and 3 unknowns. Now when I add more equation, generally it means your structure redundancy will down below 0 or becomes minus, which means your structure becomes unstable. Okay? Actually, there is another system that you guys have had before. It's a system of trust. Not trust like we trust each other. That's trust. But you have had this system of trust, right? This is a truss, looks like this. Stuff like that. A truss is also a series of axial force members put together. But at the joint here is pin joint, no moment. It's a simple system that you already have learned, so I don't mention it again in this class. And you see, you cannot use a simple system of truss and hope that it will be enough to withstand the horizontal load. That's why we need the frame for the high-rise building and you know, many typical warehouse and stuff. All right. The truss system cannot be used, pure truss system cannot be used to withstand the horizontal load because it's unstable, like this picture. Oops. Okay. Oh, geez. One moment. Oh man, it's just selling stuff. Okay, so that's kind of threw me off the rhythm a little bit. So you guys have any question about the system anymore? That I'm not sure what this silence would mean. Crystal clear?
อาจารย์ครับ
Yes, please.
at the symbol at the support นะครับ มันจะต้องเป็นสามเหลี่ยมกับวงกลมเท่านั้นหรือเปล่าครับ
I would appreciate if you could try your English. Nah? Please don't worry if you get it wrong. Try the English because as I said in the first hour, I left my Thai ear somewhere in the house, couldn't find it.
It the support symbol need to be like a triangle and circle always be like that.
See, you can speak that. Let's say the symbol is universal. Okay, it's been used for so long, and when you use it, it's generally well accepted, and everybody would understand that. Okay, a triangle would represent two forces, and a roller would represent one force. So I'd say I'm not saying like they 100% yes, but if you use this symbol, everyone else will understand you. Okay. And now you talk about the symbol. Let me show you this because I always mess this up. You know, you should know that I don't have style like this. For example, you see that's a triangle and a roller, right? So if I draw the same beam and I draw this, what difference does it make between this and that? Your question is good now because sooner or later somebody's going to ask me this. What difference does it make? We have just the vertical load, correct? Can I also draw this? Can I draw two rollers? Can I draw two rollers?
Yes.
Yeah. What's wrong with it? Why don't you draw this? Why don't you draw two rollers? You only have the vertical loads, right? Why can't we draw two rollers? Can we? As engineers, should we draw two rollers?
Yes.
Yes?
Because it have only horizontal road.
It's, you know, I understand where you're coming from. It's good. I like discussion because when we have discussion, you're beginning to think. And when you think, you don't need to remember, you know. When you think and you feel something, it's going to stay with you longer. So if you draw two rollers, this is pretty similar to standing on the skateboard, right? Am I correct?
Yes.
Yes, good. Now I'm not saying you're wrong at all. I'm just having a conversation with you. Okay. And everyone, if you want to join. So let's say I'm going to draw this. My skateboard now. And I'm going to stand on it. Do I look stable? Let's say if my weight, you know, comes down right in the middle. Do I look stable?
Yes.
I look stable. I look completely stable. And the reaction here will be just equal to half my weight. But what if there is a mosquito, flying in like this, and I say, "Hey, don't come near me." I make a movement. All of a sudden, I jerk my skateboard. Would this skateboard become stable?
No, it's not.
No, it isn't, right? Because there's a mosquito coming in from nowhere, trying to bite me. And it may cause me dengue, I let off, right? I don't, don't come near me like that. So I move. So the skateboard start to wobble a little bit. So instability can come very easily. Some, say in the chat that, yeah, now my beam can move left and right. So this is the tricky part. And I want you to grasp the concept. It can move left and right, but there is no load. It doesn't move, right? It is perfectly stable. But how could you be sure that there would be no horizontal load coming from any kind of accidents or anything at all? So generally, we are engineers. We provide safe structure. So yes, it's true, we don't have the horizontal load, but we will always draw the structure with one horizontal reaction as a symbol that our structure is always under equilibrium no matter what happens. Because this structure, this one that the green arrow is pointing at, is perfectly stable and can withstand any load, correct? So let's say if this load inclined for 5 degrees, it's still stable, correct? But this one, if this load is inclined 5 degrees, it's just gonna go roller skating. So yes, even though when we look at our free body diagram and there is no horizontal load present, we are always obliged to draw the structure to have one horizontal restraint so that we always have a safe free body diagram. See what I'm saying? That's the engineering way, folks. And now let's come back to the first question. Is it different? The beam A here, let's not use A, beam number 1 and beam number 2. Switching the roller and the hinge. What difference does it make? No, right? Because we only care about the vertical load. So we can switch the roller and the hinge around, doesn't matter because your horizontal reaction is 0. As long as we have one, and you can look at the picture of this continuous beam here. This one, you see, I only need to provide one horizontal restraint, and that would be enough. I don't need to draw a triangle every time, It's a matter of using the symbol in the professional way. But your question is really worth answering because otherwise it will be in your mind like, why? Why triangle? Why circle? Why roller? Nobody tells me. I hate that thing because I am a very curious person. And whenever somebody fails to tell me something, I'm too curious to let it go. Like, let's ask you this simple question. I'm sure Ajahn Julapot has told you at some point in time, but the perspective of you when you were like a second-year student is still not wide enough, in a way. So let me ask you this: what is a rigid body? Can anybody explain to me clearly? Why do you need to assume the rigid body in statics?
A body that can't be deformed.
Yeah, it's a body that cannot be deformed and will not be deformed. Why do we need it? Do you think it exists? Something that will never deform? It's like a Superman from the planet. What is planet? Krypton, right? Is there anything in the world that doesn't deform? If it doesn't deform, it means its strain is zero, correct? Right? If the strain is zero, stress is zero. What that is? What is that? If the stress is zero, we can just quit civil engineering. Right this minute. Do you agree or do you not agree? If there is no deformation, there is no strain. And there's no strain, there's no stress. We can just all go home, right? Why analyze the structure when there's no deformation? Have you ever thought about that?
It have a size.
Huh?
It have a size.
Size? Oh, really? I think you are thinking something, very interesting. Like size like this, tiny, like a particle. Look like a particle. Look like a bird. So you're saying when it is so small, doesn't deform?
No, I just mean it have a size, so it gonna be have a state because it have an area.
Think back to your statics. When you were involved with a rigid body, did it ever have a size?
No.
No, right? So I'm talking to you because I want you to think about it. And when you think about it, it's no reason. It's unreasonable. The rigid body is unreasonable, right? Don't you think?
I think we are trying to assume, like, if you want the beam to not change, so we should assume it to be a rigid body, so it can, like, it won't change the shape when the force acting on that beam, I guess.
Who's talking to me?
Not really.
Excuse me. I don't get your name. Can you speak louder, please? Not Varit, okay? You could, yeah, but the whole, okay, I think you're close enough. The whole point of the rigid body is that you have to understand the system of force first. So to try to make the matter simple to you, we begin with the assumption that whatever you're dealing with, whatever the system you're dealing with under force, it doesn't deform. Because deformation will cause something else. So we cannot begin by telling you, okay, you need to consider this body, and when you apply the load, it's going to deform, and then there's a strain, and then there's a stress, and then blah, 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 blah. So when they want you to concentrate on the system of force alone, they just assume a rigid body for you. And in the real world, when you go out and face a problem like this, you need to know when you can actually use the assumption of rigid body. But this is the beginning of the structure class, and I kind of love sharing. I don't know if this is going to be too far, but let's say I'm going to share one thing for you. Generally, you guys know of footing?
Yes.
Yes.
A footing is the structure that actually connects the structure above ground to the foundation that you have in place, whether it's a shallow foundation or it's a deep foundation that you use piles. Okay, so now it's this. Now it's this big foundation supporting the oil tank like this. Okay, so generally what we do is that let's say if this is like maybe 2,000 tons in capacity, you wanna use the deep foundation, the pile that is, for the system in Bangkok. You wanna know how many piles you use. So you say, let's say one pile can take 25 tons, for example. You want to know how many piles you're going to use, you divide 2,000 by 25, right? Then you know the number of piles. So on and so forth. Now, we can use this assumption, 2,000 divided by 25, because we assume that this foundation is rigid. So that every pile will carry the same load, right?
Yes.
The question is, how do you know if this footing is rigid enough? How do we know that this footing is rigid enough? Right. And that it happened before. That because generally most engineers would go on and assume that your footing is rigid enough, and therefore every part will hold equal amount of load. It's basic practice. So then when people begin to think, okay, we check the bending moment, we check the shear and so on, and it's okay. It may be okay. It may not fail under bending or shear or so on and so forth. But if it's not rigid enough, that means this assumption that every pile is carrying the same load is not true. That's rigidity. It's important. And this is kind of advanced stuff, but it should give you the idea of, when we want to make something, say, undeformable, there's such a word, we need to know how. But the rigid body enables you to go on with life with a simple assumption like this. But that's why we started off everything with the rigid body. But in the real world, it isn't. Okay. Now I'm talking about rigid body. I don't know why we got here. Why are we here talking about rigid body? I thought it was going to start on our example. Why are we here? Anyway, because somebody calls me. I love you guys asking a lot of questions. Please keep them coming. Okay. The only way that you can dig the most out of me is just by asking a lot of questions. And please use you guys senior. Your world is more widened by experience than the junior. So if you have any question and you think you want to know it now, you think it's going to help the junior, don't be afraid to ask. Okay. All right. So that is. So let us go into the example. But I think we start the second session at 10:40. So I can go on until 11:30. All right. So I have 8 more minutes. So let's not waste that. Let's go on and try to get on with our examples. Okay. I thought example 2 looks a little bit too complicated in the beginning, but so I added example 1, hoping that it is simpler. I took this from the exam some years ago, but now looking at it again, example 1 looks more complicated. So we're going to begin with example number 2. Okay. My apologies. So let's begin with this one. Okay. So now if some of you still don't grasp the idea of how the floor system works, do not hesitate to stop me and ask questions. Okay. Don't let it go. Okay. We are here so that you guys can become engineers. Okay. We are here not to embarrass anyone about why you don't know this shit and stuff like that. Okay. So let's go. Here we go. I need to erase this. You know, the fun part of being a structural engineer, one thing is that it's just to come up with the system, because generally when you look at the floor, you don't see the beams like this. The architects don't give you the stuff like this. I don't know why this, you know, series of arrows show up. My apologies. I'm going to deal with that later on. Okay. So when you have a floor, generally you're going to have a talk with architects about the locations and numbers of columns that you can have and so and so. So let's hope that, you know, columns are in place after the general agreement between all the parties. So let's look at this case. You know, you want a simple structure. You would say, hey, can I have the columns here? Even engineers can't stand that, you know. If you add more columns just to simplify your structure, this is a waste of money because you're going to have the two foundations close to each other. We don't do that. So in a structure like this, one column should be enough. Okay, but because maybe architects want to have like some effects like this, you know, the offset and so, so you end up with a structure like this. So you can't have a simple structure. You either have the choice of, you know, having the columns here at this existing location, or you want to move it there. I say this is perhaps more profitable because it reduces span length, and B3 can come into the column directly. And B5, we have the cantilever portion out to support B4. It's better than having the columns at the pin location, and this B5 becomes very long and has to support B3 before, you know, all the load goes to the column. B5 can be very, very big in this case. So I'd say this is the best system for the presented case. So now, when you look at the system, you should try to find a way for your load to go into the support as soon as possible. Okay, the purpose of the floor is to support the load, the date load of the finishing of the floor itself, and the live load. And I did not mention in the first hour that live load is the load that shows how your building is going to be used. So generally, it's another word for live load. It shows the occupancy of the building. The occupancy, well, you can say how the building is going to be occupied, how the building is going to be used. Okay, in the house, for example, it's one occupancy. Library, hospital, and so and so. Okay, so with that said, the floor will support, you know, how you're going to use your structure, and then the beams in turn will support the floor. You would have to try to find a way to transfer the load from the floor onto the beam, and the beam will move the load to the column. When the load reaches the column, it's going down to the foundation. So the job of the floor and you as an engineer for the floor system is done. Okay, so whenever you don't have the columns to support the load directly, you need to find a way for the load to go from beams to beams to beams and then to columns. And in this case, you see, we can begin with looking at the load. So it's a very simple. Now, let's say we have selected the floor and stuff, and we have selected the finishing. It's going to be the granite or whatever. So in summary, the date load is 400 kilogram force per square meter. Please notice that the load is always given in terms of load per area. Okay, and the live load, this is how it depends on how you're going to use the building. Let's say live load now is 500. So totally, the load per area now, you can say it's 900 per kilogram per square meter. And then we have the self weight of the beam. Please notice that the load now is in the unit of kilogram per meter because it's the weight of the beam. Okay. So now when you look at the B1, B1 is a simple secondary beam, you know. So it's a simple beam supporting the floor. Say this is B1, this is going to be B1, they look similar. This is going to be B1, and that is going to be B1. So when you look at the B1, it's going to have, and you know, this is the direction of the floor, right? So B1 will have to support half of the floor. Here, and then another half here. So this becomes the tributary width of B1. Okay, that is the tributary width. So when you know the tributary width, you multiply the tributary width with the load. This is one dimension, correct? You multiply with the load per area, it becomes the load per length. Just look at the dimension of the beam. You have the width here. You have the width here, and then you have the length. If you multiply the width with the length, it becomes the area, right? But we don't need the area. We need the uniform load because this will become the uniform load acting on your beam. So we are approaching the break. Let me try to finish this load for B1 first. So for B1, sorry, my B looks pretty ugly. So for B1, the uniform load is going to be equal to this 900, correct? Now the tributary width generally is equal to the spacing here. The total length here is 8 meters. You have 5 panels. Each is 1.6 meters. So if this is 1.6, the half distance between each beam should also be equal to 1.6. Some students will get confused, especially when you are under duress. Yes, the exam, right? And mess up this tributary width, which is like the easiest thing in the world. But ladies and gentlemen, when you mess this up, you mess up the load. So you would understand my point of view on this, right? So this is the tributary width of 1.6. This plus 300 up. Plus 300 should give us the total uniform load acting on our beam B1. Okay, so I'd like to stop the session now so you guys can have a break before we can come back and finish this. So I think I'm going to stop the record first so that you can ask questions more casually.